This is the most inclusive course on cotton fiber to fabric quality and manufacturing. It reflects more than 30 years of experience by one of the top scientists and utmost experts in the field of cotton research and textiles. Please be aware that what you will see is only very small pieces of some parts of the course. This course is over 40 hours in total. As you will see, the course uses direct teaching by the speaker, slideshows and real videos of all processing from harvesting and ginning to spinning and weaving. The course comes with all videos and hard copy of slideshows. An e-copy of one of Dr. Elmogahzy books also come with the course. Again, these are only few clips. A complete course should be ordered via Amazon.com using the title, the author, and the code number of the course.
The first part of this course is an introduction of critical concepts of fiber to yarn engineering and cost optimization. The second part deals with fiber characteristics such as fiber fineness, fiber length, fiber maturity, fiber strength, neps, and cotton stickiness. The third part deals with yarn characteristics such as yarn count, twist, strength, irregularity, and imperfections. All characteristics are discussed in the context of measurements and impacts on fabric quality. The fourth part deals with fiber processing, starting with harvesting and ginning and going into cotton mixing and blending. All stages of spinning preparation including opening and cleaning, carding, drawing, combing, and moving are covered in great details. Different types of spinning such as ring spinning, compact spinning, rotor open-end spinning and friction spinning. The course will also cover effects of yarn and fiber characteristics on textile fabrics.
Air-jet spinning. Well, as the name implies, when we say air-jet spinning, it is air that represents the main media to make a spun yarn. The idea of air-jet spinning is an old one that was initially developed by DuPont, if I'm not mistaken, in the early 60s, toward air texturing or texturizing. So the concept of flying fibers into the air for the purpose of creating wrapping or twisting of the fibers is a very old idea. The history tells us that DuPont invented and developed the concept, but they really could not market it for one reason or another. And as a result, the Japanese, mainly the Murata Corporation, was able, or the Murata Corporation was able to take that concept and fly with it into the stable fiber yarn manufacturing. The idea is unique. You have fibers floating in air, okay? And when the fibers float in air, and we've seen that in rotor spinning, the air is typically exhibits a turbulent airflow. Okay, there is no ideal laminar airflow. But that turbulence is in air-jet spinning is the key feature. You've seen in rotor spinning, we try to avoid the turbulence. We try to increase the pressure or the vacuum of the air in the air duct for the purpose of orienting the fibers coming out of the opening roller. Because we definitely wanted a laminar airflow in case of rotor spinning. Now in air-jet spinning, we intentionally aim at turbulent airflow. And that turbulence is basically introduced via tangential feed. Okay? If you can look here, you can see that we are feeding the airflow via tangential inlets or orifices or nozzles. Now, also note that there are some fibers here that are separated from the fiber flow, from the sliver as it's fed. So really we are talking about two key issues here. First of all, the fiber strand going into air-jet spinning is not or does not exhibit a continuous flow. Instead, some fibers are being separated. How they are separated, we will discuss that shortly, but they are separated by air turbulence. So we want the air to first separate some of the fibers, few fibers, from the mainstream of the fiber strand. That's why we put it under the category of interrupted spinning. It's not a continuous flow. It's not completely interrupted, such as the case in rotor spinning, but instead it's partially interrupted or partially separated. And the tangential airflow that we see here is achieved to produce a turbulent airflow through which the fibers will be twisted, because those straight fibers now, as soon as they face a turbulent rotating air in this area here, okay, what they're going to do? They're going to twist, they're going to wrap. So that is the basic components of an air nozzle. Fiber inlet, airflow nozzle with turbulent airflow via tangential feed. Now that's all. The fibers coming out of this nozzle, unless we hold them somehow, they will go back to normal. They will be straight. So this whole operation is considered as a false twist unit. But if it is false twist and the fibers are coming out back to normal straight fibers, how are we going to achieve a yarn integrity? How are we going to achieve a yarn of some strength? Those fibers that have been separated early by air effect are now going to join the fibers coming out and wrap around them. Look at this. Very simple principle, yet it's never easy to fly fibers into an airstream. So once again, the principle is very simple. We feed in fibers that had to be, of course, opened and reduced to the desirable size of yarn, number of fibers per cross section. And as we feed them, we separate some. We call this the end opening action. You're gonna get very familiar with this term as we go along. So that's the end opening action, which is carried out using air turbulence. So we disturb the fibers at the inlet to separate some, and then we tangentially feed the air. Okay, so the fibers will curl or wrap or twist, but then the produced fiber strand is parallel fibers again. That's the core, And what it is that the separated fibers in the top are joining the fiber strand one more time to create wrapping or built fibers or belly fibers. Now, we just mentioned belly fibers and built fibers as being defects in case of rotor spinning that were unwanted. Well, belly fibers and the built fibers or wrapping fibers in case of air jet spinning are desirable, wanted, and intentionally introduced. So you can see the key features here or the key differences. In open end, we have an air duct, yet we want the fiber to flow smoothly and the fiber to be oriented, so we want a very laminar airflow. In air jet spinning, we still have an air duct or air nozzle, but we intentionally make the air flow in turbulent fashion so that we can wrap the fibers and we can separate some of the fibers. And in open-end spinning, we have built fibers or belly fibers that were unwanted, that happened as a result of the overlap between the inlet fibers and the output peeling point. In air jet spinning, those fibers that are separated, we want them intentionally to wrap around the yarn to hold the core. Indeed, this is the only source of strength in air jet spinning. So we have twisting, but it's false twisting because those fibers will come out straight again. And then we have end opening action. So there are two very unique mechanisms that are involved in the make of air jet spinning. That is as simple as it can get to explain the principle of vortex spinning or air jet spinning. Here is a typical machine where we have sliver being the input strand. That sounds familiar, like open end. But what is unique here is we have a drafting system. That's a roller draft. So we are not using an opening roller here. Okay? Recall that in rotor spinning, we've used an opening roller to reduce the size of the sliver down to few fibers, 2 to 10 fibers maximum. Here we don't have to do that. We're using a sliver which has 20 to 40,000 fibers per cross section, and we're using a roller drafting system. And of course, Murata has developed the roller drafting to the extreme state of the art to be able to handle that heavy sliver going in. And then we have a massive fibers coming out after drafting, but the entire main draft already happened. So we have, by the time we are here, we have reduced the fiber strand down to the desirable number of fibers per cross section. So there is no further reduction in the number of fibers per cross section as we go to the air nozzle, which is the consolidation zone here. So we rely on roller drafting to entirely reduce the size of the fiber strand down to the size of the yarn. And then we use air after that to do the consolidation. And once again, we're breaking the link between the consolidation and winding, because winding is happening after that. It's completely separate unit. And as a result of that, and just like open end, we can make a very large package in air jet spinning. Now the point I'm trying to make here is, in case of ring spinning, the rotating component was the spindle or the package. In case of open-end spinning, the rotating component was the rotor. So as a result, in ring spinning, we have a spindle or a package running at maximum 25,000 RPM. As we went to the rotor spinning, we had a small rotor that was running at 150,000 RPM. What a jump. Now in air jet spinning, the rotating media is air. And the air can rotate, which air is tangentially fed via nozzle. These are 0.4 millimeter diameter. These are very, very small nozzles. And as a result, the air, the tangential air feed can rotate at in order of millions We're talking about 2 to 3 million RPM. Obviously, the fibers are rotating with the air. So due to the air drag, those fibers are estimated to rotate at about 200 to 300,000 RPM. And that is a huge jump from 25,000 RPM spindle rotational speed and ring spinning to 150,000 RPM rotor speed and rotor spinning to now we're talking about 200 to 300,000 RPM in air jet spinning. What a huge jump. Indeed, delivery speed wise, and we told you the relationship between the rotational speed and the delivery speed, air jet spinning is the fastest spun yarn forming system ever made so far.